Imagine somewhere in our universe an utterly strange world. A place where time could both speed up and slow down. From where we could journey into the past and the future. Somewhere time could even split in two. Incredibly, this is no alien world. It's our world, and it's all around us. We live in a world governed by time. From the tiniest of cells to the most distant of stars, our entire universe is subject to the beat of a constant clock. And because time is everywhere, we think we know it. We know that it's regular and it moves in one direction. We know that it's universal and eternal. And we know that it never, ever stands still. But how can we be so sure? How much of what we think we know about time is really true? In this program, I want to get to the bottom of what time really is. And in doing so, I'll be challenging some of our most cherished beliefs. As a theoretical physicist, it's this hidden time that has always fascinated me throughout most of my professional career. I'm going to explore the very limits of our universe in order to uncover just what time really is. And in the process, I'll be revealing an astonishing secret, nothing less than our ultimate destiny, the future of the universe, and the fate of time itself. Of all our assumptions about time, one of the most obvious is that time is regular. That a minute will always be a minute. For everyone, everywhere. Here in the Swiss Alps, I'm searching for something that challenges this assumption. Something that, if time was as regular as we think it is, shouldn't exist at all. And this is what I've come to see. It's a particle counter, telling me that the air around me is full of tiny particles called muons that come from all the way out there. Muons are short-lived particles formed when cosmic rays from space collide with the upper atmosphere. But the big mystery is how they come to be down here on Earth. Because, with a lifespan of just 2/1,000,000th of a second, muons should only live long enough to travel a few hundred meters. And yet, here they are, after a journey of several miles, something that shouldn't be possible. So what exactly is going on? The answer to this mystery, the reason why muons can reach us at all, is so extraordinary that from the moment it was first proposed, it literally rewrote the rule book of time. Less than 100 miles from the Alps lies the affluent city of Bern. In the early 1900s, this was home to a young German physicist who would change the way we looked at time forever. His name was Albert Einstein, and he's been my hero for the past 50 years. In 1905, in this, his first-floor apartment, Albert Einstein put the finishing touches to his radical new theory: special relativity. One of 5 papers published by Einstein in 1905, special relativity would make us think about time in a completely new way. Einstein's astonishing claim was that time was not regular at all. It could beat at different rates. Time changes, depending on relative speed. Imagine for a minute that my tram is capable of traveling at phenomenal speed, just a fraction less than the speed of light. According to special relativity, the rate at which time flowed on this speeding tram would depend on whether you were on board or looking in from the outside. So while for me, it would seem as though time was passing perfectly normally, for me, sitting on the pavement, assuming I could somehow peer inside the tram, time would assume a totally different quality. Looking in from the outside, I'd sense that time on board the tram was passing much more slowly. That's because, according to Einstein, the faster an object moves, the slower its time will run to someone observing from the sidelines. In other words, time can vary. It's all a matter of speed. And that explains the mystery of how our muons reach the Earth. Because muons travel near the speed of light, relative to the Earth, their clocks have slowed down. So much so that they exist long enough to reach the Earth and be detected. Time for our muons has stretched. It beats very differently to the way it does for us. Now, the effects of special relativity are so small that they have no impact on our daily lives. But the fact that they are there at all has changed everything. Because if time is relative, if time is flexible, then our belief in the immutability of time is wrong.